In this series of videos, we're going to see how we can compute the eigenvectors for a matrix and why we use the process we do. If we start with the eigenvalue-eigenvector equation, remember that is that whatever a matrix is, we have an eigenvector if doing that transform by A is the same as multiplying just by a simple scalar. So it's some vector that if we do matrix multiplication on it, it turns out it's not really complicated for this particular vector. It is simply the same as multiplying by a scalar. Well, we saw earlier that these calculations are easier to work with if we turn this right-hand side here, instead of just to a scalar times a vector, if we now have a matrix the same as we had a matrix over here. And what we can then do is take all of this side, move it over. So we get A times V minus lambda I times V equals the zero vector, or A minus lambda I, that same matrix we built earlier, equals the zero vector. And remember, for this case, we're now looking with a specific eigenvalue in mind. So we know all of this, and we want the vector V. And so all we have to do, hey, that's a system of equations, right? Some matrix times V equals 0. That means we just need to solve a system of linear equations. And we've done that before. I'll just remind you, for a non-zero vector V, the zero vector will always work. It's one of those things you have to keep catching yourself on, especially when this is new. We want a real direction that's being scaled by this matrix, and the zero vector doesn't get scaled by much. It always stays zero. And also mathematically, the zero case is always going to satisfy this, so who cares? We want the more interesting cases, the non-zero vectors V. Let's see this in an example, working with the same matrix we saw earlier for the 2 by 2 case. We already found the eigenvalues for this particular matrix were 4 and -1. And so we take each eigenvalue one by one. Oops. Take each eigenvalue one at a time. So let's take lambda equals 4. Let's call this lambda 1, because that's our first lambda. That'll contrast with our second lambda, -1. The condition we're setting up is that A minus lambda I times V is equal to the zero vector. And we know all of this now. Remember, if lambda's 4, we know A, we can write that out actually. It's going to be 5, 3, minus 2, minus 2. I'm going to do this again in gruesome detail. You can take some shortcuts. You can do this in your head if you like, but I just want to make it clear what this minus lambda I is doing. If lambda is 4, we're going to subtract specifically 4 down the diagonal for each of these things. And our vector V, we're trying to solve for it. So V is unknown. And it's going to have components. We're going to need to solve for the components. And so let's call it A and B. 2 components for a 2-dimensional vector. So we'll have this times AB equals 0, 0. Well, that we can tidy up. This is -1, 3, oh sorry, it's +1, 3, +1, 3, and -2, -6, AB equals 0, 0. And you should see, you must see it. Freaks people out to see when it's new, but this is totally predictable. This matrix here, you can see, is a column and another column that's just a multiple of 3, right? So this is not invertible. And that's a good thing. That's exactly what we have to have happen. This is a check, in fact. Remember, if this matrix were invertible, the only answer to some vector equaling 0 is the zero vector. Well, I don't want a zero vector. I want a real honest-to-goodness direction out of this. The only way we get a real honest-to-goodness direction is if this matrix is not invertible. If the kernel is not just the zero vector, if these columns are not linearly independent, all the good stuff we've seen before coming back again here. Another thing we should note, though, is there are an infinite number of solutions. And that is clear. You can imagine if the answer was like 1, 4, well then doubling that would also satisfy this equation, because the kernel is a subspace and all the vectors in the subspace will be multiples of each other here. All we're going to do is find one of the solutions, and it'll be a basis or a sample vector that we can use in our solutions. All right, how do we do that? Let's get a vector for real. Because these rows are actually duplicates of each other, what we can do is just capture one of them. So we can just say that a plus 3b equals 0, or a equals minus 3b. The upside of this is that we get to pick some value. We have an infinite number of solutions, so we get to pick one of these numbers, and then we get the rest of the vector. So here I'm going to pick b equals 1. You might have picked a equals 1. It does not matter. As long as you pick one value and use the equations to constrain the rest of them, it'll be a perfectly fine eigenvector. So we pick b equals 1, and that gives us a equals negative 3, and that gives us v1. I should actually have labeled that earlier. This is v1. The one that goes with the lambda 1 is going to be a first, negative 3, b second, 1. So for lambda equals 4, we get the vector negative 3, 1. Now we just repeat the process, hopefully a little more quickly and efficiently, with lambda equals negative 1. So we set up our equation again. A minus lambda I, this time times v2, is equal to the 0 vector. We have our A matrix here again, and so I'm just going to put that in, 5, 3, negative 2, negative 2. Explicitly subtract the minus 1s along the diagonal, minus lambda I, but the lambda is also negative, so we get double negatives here. And I'm just going to put A and B in here again, 0, 0. And tidying that up, that gives us 6, 3, negative 2, negative 3, no, negative 2, negative 1. Ah, there we go. There's our check again. These rows are multiples, or the columns are multiples. So in our check, this is not invertible. That's exactly what we want. So we'll give ourselves a check mark for that. And then we can start solving for the equation. So this is going to be redundant. Let's take the easier of the two equations. Let's go minus 2a minus b equals 0. And so let's bring the b over. Negative 2a. Again, there will be an infinite number of solutions for this vector, but they'll all be multiples of each other. So you just pick some value. Let's pick b equal to 1. If we do that, then, oh, actually, what am I doing? That looks harder. Let's pick a equal to 1, because then we can find b really easily. Sub in the one that's not isolated. B is equal to negative 2, and that gives us v2 is the vector a is 1, b is minus 2, like so. So for this vector, it goes with this value. And now we have a complete summary of what A does as a linear transform. Along the vector, which was last page here, along the vector negative 3, 1, let's label this here, v1, negative 3, 1, A scales vectors by 4, and along v2, the direction of 1, negative 2, this A matrix scales vectors by negative 1. Or if you like, it flips them, inverts them. And again, this matrix, complicated. Look at it going, no idea what this does. A perfectly equivalent form to understand what A does is along these two vectors here, which are enough to make a basis for R2. We know what happens along V1, we know what happens along V2, and any other vector we care to pick can be a combination of those two vectors. And so the direction of this gets scaled by 4, and whatever component here gets flipped, we can predict exactly what happens to any vector because we know what happens to these two basis vectors when we multiply by A.